Bright Tuty. Every student matters.
Now, a very important discussion is we have said that the acceleration due to gravity does not depend upon the mass of the object. So, whether I am throwing or I am dropping a light object or a heavy object, it should remain same. It should be reaching the ground at the same time. But do we see that in our normal life? If I just try to take an experiment, I will do an activity, I will drop a stone and I will drop a feather. Will they reach the ground at the same time? No. Then does this acceleration due to gravity concept, this is having some exceptions or something? It is not like that. Actually, Galileo, we must have heard the name, he performed the experiment and he threw these objects from the Leaning Tower of Pisa. And he concluded that both the objects landed on the ground on the same time, and if there was a time lapse between the stone and the paper or feather or any light object, then it was not because of the difference in acceleration due to gravity, but it was because of very important thing, that is air resistance. A lighter object or an object having a greater surface area or an object having a lesser density, that will experience more air resistance. So, if I throw a stone and a feather simultaneously, the heavier object, the stone, reaches the ground first and the paper or the feather, the lighter object, reaches the ground later, right. But this is not, I repeat, because of acceleration due to gravity, it is because of the air resistance. Got it? So, if I do something, an activity of some sort in which I do this experiment in vacuum, then surprisingly they will reach the ground on the same moment. So, they will reach the ground within the same stipulated same time period, correct, together, because the acceleration due to gravity is acting on them at the same rate. Got it? Let us see this activity through the help of an animated video. You will be able to understand better based on what exactly you will be relating. Now, let us see this feather and coin experiment. Now, in this experiment, we will be requiring certain material, right. What exactly will be requiring? We will be requiring a feather, we will be requiring a coin, and we will be requiring a long glass tube. Now, there is a vacuum pump which we use to create vacuum. Let us see the procedure first. How we are going to do the experiment? We know that almost all bodies near the surface of the earth fall towards the earth when released, whether stone or apple or any particular thing. However, earlier it was thought that the heavier of bodies fall towards the earth more rapidly than the lighter one. The familiar example was that of a feather and a coin that we have discussed earlier. It was noticed that the coin falls downward towards the earth more rapidly than the feather when dropped from the same height. However, Galileo did not agree with the idea that the heavier the body, the more rapidly it fall towards earth. He dropped one stone and a feather of different masses from the Leaning Tower of Pisa and showed that they reached the earth at the same time. And he explained that the feather took a longer time to reach the earth because it had a large surface area and hence encountered more resistance due to air as compared to the coin. So, the feather slowed down due to air resistance and not because it was small or it was light. Later on, Robert Boyle created vacuum in a long glass tube and then allowed the feather and coin to fall simultaneously. And wow, what we saw, that both of them reached the bottom of the tube at the same time, therefore proving Galileo. Thus, to conclude, we can say that the acceleration produced in freely falling bodies is the same for all bodies irrespective of their masses. So, whether it is a coin, a stone or a feather, all of them are going to reach the ground at the same level irrespective of their masses, provided there is no air resistance, provided there is basically no kind of obstacle in the form of air resistance. If there is a vacuum, then this experiment will hold good, and this shows that acceleration due to gravity applies on all the objects in one go at the same level, thereby causing acceleration due to gravity to be 9.8 meter per second square. Got it? Good. I hope you have enjoyed the video, and now you must have understood exactly what I meant to say. Fine. Now, there is very one important thing, that we have said that acceleration due to gravity is calculated by the formula capital G capital M upon d square or r square, right? Fine. Where d is the distance, and when we talk about earth, we can also write it like capital G capital M upon capital R square, because now we are taking the distance to be the radius of the earth. Fine. But one important question, is earth a perfect sphere? Is earth perfectly round? No, we know that it is not. The earth is not perfectly round, it is like this, right? It is not a perfect circle. So, if I am talking about the center of the earth, then these are the two poles, north pole and the south pole, and this be the equator. So, if I relate, then the north pole and the south pole, the distance or the radius is comparatively lesser as compared to the equator. So, there must be slight variations in the value of acceleration due to gravity in different places. Why? Because the radius is not same throughout at all the places on earth. So, when I talk about the poles, from this equation we see that the acceleration due to gravity is inversely related to the radius or the distance. So, if the radius is less, then in that case the value of acceleration due to gravity will be comparatively more, and this is what happens at poles. At poles, the radius of the earth is comparatively lesser, therefore, the value of G is slightly more than 9.8 meter per second square. And if I talk about equator, at equator the radius is slightly more, because of which the value will be lesser at the equator. So, practically the value of acceleration due to gravity, if we are talking about earth itself only, the value of acceleration due to gravity is not constant throughout at all the places on earth, right? It varies depending upon the change in radius, but for practical purposes we will everywhere in the numericals will take the value to be 9.8 meter per second square only. Now, students, because I have just initiated the talk of numericals, let me tell you one more thing quite importantly. When we are solving the numericals, then in some numericals the value of G in the bracket, it is given to be taken as 10 meter per second square, rounding it off in order to make our calculations easier. But let me remind you, we have to take G is equal to 10 only and only if it is given in question. If the value of G is given in the question to be taken as 10 meter per second square, only then we are going to take it to be 10 meter per second square. Otherwise, if the value of G is not given in the question, you can never or you should never take it to be 10, you should always take it to be 9.8 meter per second square only. Got it? Fine. So, this is the value of g changing at poles and equator, but generalized way most of the times we will be taking up as 9.8 meter per second square only, right. Now, the laws of equation that we have studied in the motion chapter, you must be remembering that the equations of motion we have studied, there were three equations of motion. The first equation of motion said that V is equal to u plus at. Remembered? The second equation of motion, yeah, now it is coming up, huh? I know you know, good. Second equation of motion said that S is equal to ut plus half at square, and the third equation of motion said that V square is equal to u square plus 2as, right. Now, when we talked about the equations of motion, remembered that when we did the numericals, I also told you about some important things. What? We said that whenever a body starts from rest, whenever a body starts from rest, remember what we did? We took u to be 0, the initial velocity of the object was taken to be 0, right. Similarly, whenever a body stopped, whenever a body stopped, then in that case we always took final velocity to be 0. Third important thing, what we learnt and practiced there was acceleration was taken to be positive if the object was speeding up or it was accelerating, and the value of acceleration was taken to be negative or it was taken to be retardation whenever the object was slowing down or retarding. These were the three things that we studied in equation of motion. Now, students, these equation of motion also hold good in case of force of gravity, right, but there is a slight difference. This basically is a kind of linear motion in a straight line, horizontal, but when we talk about gravitational force, it is because of gravity, right. So, this is basically not linear, but it is horizontal. Fine. So, when I talk about horizontal, then there are a few things that I can relate. First thing is, now instead of using A, I will be using acceleration due to gravity, because the force or the velocity whatever is impacting the object, that is because of the gravitational pull, and the acceleration is caused due to gravity. Second change, it is not exactly a change, it is a normal thing that we know, that when I talk about the linear motion, I talk about distance, but the same distance when I relate, right, in horizontal. So, I can equate it to be the height. It is one of the same thing, not much difference about it, but simply the distance in the upward or downward direction can be called as height. So, if I want to, I can see these three equations written in this way also. The first equation can be written as V is equal to u plus g t. Rather than writing A, I can write g, right, because now the acceleration is because of gravity. Second equation, now I can replace S with h. So, I can write h is equal to ut plus half gt square. Now, I have made two changes in it. One, I have replaced the distance with height, and I have replaced the acceleration with acceleration due to gravity. I hope I am permitted to do so, right. We can do it because that is one of the same thing. And the third equation of motion, again making the same two changes, v square can be written as u square plus 2gh instead of 2as, replacing a with small g and s with h. Got it? So, now in the case of gravity, in the case of upward downward motion, we can say that the equations of motion may be written as this, one or the same thing, right. Now, very importantly, when we will be attempting the numericals based on these, now we will relate these important points. What? First point is, whenever, this is very important, you need to take care, please try to relate, whenever a body falls down or is dropped, whenever we drop a particular object from some height, we will take the initial velocity to be 0, because when we are dropping it, that means we are holding it and initially the body was not moving, right. So, the initial velocity of the body is taken to be 0. Second, very important thing, whenever a body is thrown up, whenever we are tossing an object or throwing a body in the upward direction, then we will take its final velocity to be 0. Now, why so? Because with whatever force, with whatever velocity you throw this particular object, it will gain a certain limited height, and after that it will just stop for a fraction of second, and from there it has to fall back to the ground. So, at one stage, at one extreme point in its particular, whenever we are throwing it, at one point the velocity has to become 0, the body has to stop, because from there it will fall down under the force of gravity. Got it? Now, third important thing, whenever we are dropping an object, so the object is falling under the force of gravity in the direction of force, and it is accelerating, the value of g is of course 9.8 meter per second square, but we will take it in positive. Why? Two reasons. First, it is accelerating, speeding up, because free fall is an accelerated motion. Second important thing, it is in the direction of force of gravity. But whenever we are throwing an object in the upward direction, then the acceleration of the gravity is of course 9.8 meter per second square, but it is the ball, the object is now going against the force of gravity. So, the force of gravity is working against it. That is why it has to be taken as negative. Very important thing. Whenever you are throwing an object in the upward direction, you will place a negative sign in front of acceleration due to gravity. Correct? Now, the fourth point, which may be at first instance we do not accept it, actually we do not believe it, but this is a fact, that the time taken by the object which we have thrown, so time taken for going up and while coming back, the time taken by the object is same. Now, this is something that students do not actually believe at once. They tend to calculate, they tend to do it practically. You may do it, but this is just such a small time, you will not be actually related practically when you are throwing a ball up in the air, and you will relate the normal gesture. The normal understanding is that while it is coming back, it is speeding up, and while it was going up, it was taking more time, but it is not the case. Theoretically, believe me that the time taken by that object to reach a certain height and coming back, particularly from that particular height, that is always the same. Got it? So, these are the four things that you need to remember in the equations of motion, so as to attempt the numericals based on this topic. Fine. Okay.